Okay, so in this case, I'm giving two events. The first event here is female with a probability of 52.6% because the percentage of females in the adults representing the probability when you select one female from adults. Okay, similarly, we have another event which is left-handed people or left-handed adults, and they have this percentage 9.5% of adults are left-handed. That means if you select one from all adults, then the percentage that it will be left-handed or the probability it will be left-handed is exactly the same as a percentage, which is 9.5% or 0.095. Okay, so and we have another event here, left-handed females. Left-handed females, if you notice, it combines both the females and the left-handed together at the same time. So together at the same time, the 5.3%, this is a percentage of left-handed females. What is left-handed females? Is it the females or left-handed? Is it the females and left-handed? Which one is it? Which one?
Uh, and
The and, very good, the and. Because sometimes the word and is omitted. When I say A, B, I actually mean A and B. Okay? So in this case, left-handed female means left-handed and female. So I am giving the percentage of the and, or I'm giving the probability of the and. So what is left here from this equation? The or. He gave me the A, he gave me the B, he gave me the and. If I apply this formula, then I can easily get the probability of the or, and that's exactly what the question wants. The question says, find an adult selected at random from the city, for an adult selected at random from the city, find the probability that the adult is female or left-handed. So he is asking about the probability of the or. So all what I have to do, I'm just going to use the percentages given in the question and substitute in this equation. So I'm going to say 52.6% plus 9.5% minus 5.3%. And this will give me the probability, of course, as percentage, because we're using percentage here, so the result will come as percentage. Or you can convert all these percentages to ratios and work with ratios, and the end result will be also a ratio. Okay, so if you look at the answer, I just have the final answer here. I didn't actually do the steps, but if I open my calculator and I can show you how this is done, I'm going to say here now the 52 plus 6 plus the 9.5 minus the 5.3, which is and. This will give me 56.8%, and 56% means if you divide it by 100, this will give you the ratio. So the ratio is 0.568, and I'm writing the answer here as ratio because usually probabilities are given as ratio. Okay, is that clear the idea? So here is direct application on the rule. The only difference is that you have to realize that percentages and populations or represent probability, or the probability actually can be represented as a percentage. So when you select one person from the adults, the chance of the probability being female is exactly the same as the percentage of females in the population of adults. Okay, clear that first question? Anyone have any concern here? Type. The next question is probably totally different. Okay, I didn't give you percentages of A and B, but I give you Venn diagram, and from this Venn diagram you can tell how many in A, how many in B. So I didn't give you the percentage of the first event, second event. I give you a Venn diagram for A and B, and Venn diagram of A, as you can see, has 3 outcomes, which are 4 and 5 and 6, while the event B in this Venn diagram has 4 outcomes, which are 5, 6, and 7, and 8. And I'm asking you again the same question, which is, what is the probability of A or B? A or B. So in this case, I'm going to use classical probability to get the probability of A, which is 3 over the total. Of course, if you count how many outcomes we have, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, so the total number of outcomes is 10. And A has 3 of these 10. So the probability of A is 3 over 10. Similarly, the probability of B is 4 over 10 because it has 4 outcomes and the total is 10, right? And in the and, we said the and is the common part, the shared part, the intersection, which has 2 outcomes, 5 and 6. So this will be 2 out of 10. So we can apply this rule again, and we say 3 over 10 plus 4 over 10 minus 2 over 10. But the question is now, do you think we really need to apply the rule? The question now I'm asking you, do we really need to get the probability of A and get the probability of B and the probability of the and then you apply the rule? Or we can just look at the union of A and B together and count how many outcomes the union have. What do you think? Which is faster?
We can look directly at the diagram.
Yeah, we can directly look at the merge of A and B, the union of A and B, and count how many there, which is 4 and 5 and 6 and 7 and 8. And just count them, there are 5 outcomes. The total is 10, so the answer is simply 5 over 10. We can think of A and B together as one big event. If you think of A and B together, the union of A and B as one big event, the one big event has 5 outcomes, 4, 5, 6, 7, 8. That's it. So the answer simply will be 5 over 10, and we don't even need the rule. And that's maybe my point today. In many cases, we don't need the rule, because we can feel the merge, we can feel the union, and we can know the outcomes there, and we can just count them, and then we can get the probability. We don't need the rule. So the rule is used sometimes, and sometimes it's actually not needed. You can still use it, but it's not needed. All right. So here the answer is quickly 5 over 10 or half or 50%, and which can come from the rule, or we can actually come from the just counting the number of outcomes in the union of A and B. Okay. So that's another example where I had a slightly different type of questions. Okay, so let us see what other questions we have. Question number 3. Now say a die is rolled. What is the probability of getting an even number or a prime number? Okay, so here I have 2 events. One of them is even and one of them is prime. So, and I want to get the union. So if I want the union, it's maybe useful to list these, write them together. Let's think of the even. What is the even? Let's just write that. Okay. What is the even numbers that are in the die? How many even numbers?
2.
Yeah, 2.
2, 4, 6.
2, 4, 6. How about 8?
No.
2, 4, and 6 only, because this is the die. So this is the event that has even number. Okay, the event that has prime number, prime numbers actually start from 2. Let me just give you this tip. Prime numbers start from 2. So, but what are the other prime numbers that are in the die? I hear someone saying 3, right?
And 5.
And 5 also.
5.
Yeah. So 2, 3, and 5. 7 is also prime number, but it's not in the die. The die is only from 1 to 6. So if we merge them together, you can imagine we can still apply the rule here, but let me just imagine that we're just merging them together. So what will be the merge? What will be the even union of prime? It will be 2.
2.
Yeah, and then 3, and 4, and 5, and 6, right? All these numbers are in the merge, correct? Shall I write 2 again or no need? Yeah, 2 is shared already, and we don't write the shared outcome twice. We don't repeat outcomes in the union, because this 2 is exactly the same as this 2. We have only 1 2 in the die. Look at this. This die has only 1 2. It's not 2 2s. Yeah, it's only 1. So we write it only one time. It's one particular outcome. So that means in the union we have how many? 1, 2, 3, 4, 5. We have 5 outcomes. So the probability of the union, which is even or prime, remember the or indicating the union, and this symbol you remember is also a symbol of union. So the or will be in this case 5 over 6, and I didn't even need to apply the rule. But if I wanted to apply the rule, I can apply it. So let us solve this question another way when we apply the rule. Okay, the other way with applying the rule will be having the probability of even plus the probability of prime Okay, don't know why it's doing like this. Minus the probability of even prime. Okay, or even and prime. So the probability of even we have seen is 3/6. The probability of prime we have seen it also 3/6. But how about even prime? Even prime means the common part. This is the common part, which is 2. This is and. This is the intersection. Right? That's when they are even and prime at the same time. Which number is even and prime at the same time? Only one number. Okay, only one number, which is 2. One number which is 2, so we are counting to get the probability of 2, which is 1/6. This way we're getting the same answer, which is 5/6. So when you applied the rule, we got the same answer, which is 5/6. Okay, clear now? Maybe I can just write this note that the probability of even, or maybe actually the even prime is only the 2. Okay, is only the 2. The even prime is only the 2, which is one outcome, so 1/6. So that was another example of how we can use the addition rule, or sometimes we don't need the addition rule, but the concept of the OR has to be clear. Okay, clear now? So here I wrote the answer with the addition rule. So that was another example of applying the addition rule. Now, let us see one more question and see what will happen. Okay, this question is different. This question we have a table. It's called the two-way classification table because here people are classified in two different ways. One way is the gender, the man and women, and the other way is certain property they have or certain adjective or some quality or something like that. So here, this is related to their smoking habits. They either smoke or they don't smoke. So we have the total number of people here. You can tell by adding all these frequencies. This is more like a frequency distribution table, but again, the frequency is distributed in two ways. One way on the gender and one way is the smoking habit. So the total number is 43 plus 50 plus 31 plus 40. So we can easily get the total number of people in this table by just adding all these numbers, just like n 43 plus 50 plus 31 plus 40. That will give you the total number of people here, which is 164. Okay, so the question is asking, if one person is selected from this table, what is the probability the person is a man or a smoker? So the men together, how many men here we have? How many men?
93.
93. Okay, how many smokers?
81.
50.
No.
Yes.
Yeah, 81. Smokers are 81. So if I merge the men with the smokers, does it mean I have to add these two numbers that you both mentioned? I have to say 93 plus 81? No. Why is this? No, because there's 50 smokers who are at the same time men. So 50, you cannot count it twice. You cannot count the 50 one time with the men and count it again with the smoker, and you say, okay, this is the merge, this is the union. No, in the merge, in the union, we don't repeat elements. In the merge or in the union, we don't repeat elements. That's why you can get the union, the man or a smoker, without using a rule, by simply adding these three numbers: 43 plus 50 plus 31. Okay, so that's what I'm going to do now. I'm going to add 43 plus 50 plus 31. And this way I got the total number in the union of men and smokers. Here's all the men, here's all the smokers. Together they are 43, 50, and 31, which is 124. Now, if I want to know the probability the person selected is a man or a smoker, then I have to divide this number 124 divided by the total, which we said before, what 46 is it? 164, I forgot.
4.
Yeah, 164. Okay, so that becomes now the probability for selecting a person who is man or smoker. Okay, I didn't have to use the rule here. I just look at the union. Again, it was obvious to me, it was clear when the men and smokers merged together how it would look like. And when I looked at this, I was able to count how many outcomes in this union and how many total, and then I divide it. So this is the answer very simply. Right. Another way here, now I think I did the same thing here. In my answer, the same thing. I added the 3 numbers up and then the 4 numbers down, and this gives me 124 over 164, which is exactly what I did now. But suppose I want to do the rule. If I wanted to do the rule, can I use the rule? Yes, I can use the rule. Yeah, it may take a little bit more time, but yes, you can apply the rule here. So in this case, let me just open a small window for the possibility if I want to apply the rule. Okay, so if I wanted to apply the rule, I would say that he wanted the probability of being a man. I don't know why the pen is doing this. Okay, probability of detecting a man. Let me just write slowly. Or smoker. So according to the rule, it will be the probability the person selected is a man plus the probability the person selected is smoker, and then minus the probability that he is a man and smoker. So the probability of selecting a man comes from the total number of men, which we said before, 43 plus 50, and we divide this by the total, which is 164. The probability of smokers comes from the total of the smokers, which is 50 plus 31 divided by 164. Now the men and smoker means the intersection of when they are both happening at the same time. Where is the men smokers? The men smokers are only 50, so that would be 50 over 164. And if you calculate this, this will give you the same answer as we did before. This will give you the same answer as we did before if you would like to choose to use the rule. Okay, clear now. So that was question 4. Different experience, different story, different scenario for applying the addition rule. But we have seen 4 questions so far. Let us see more. Let us see more. Is there more ideas? Yes, there is more ideas. Type. Here, a sample of 100 wood and 100 graffiti tennis rackets are taken from the warehouse. This question I had yesterday in my class, and a lot of people keep asking me about it. Type. What is the challenge of this question? The challenge of this question that the information you need is not given directly. Okay, like here in the previous example, the table, all the numbers are in front of you, right? In this example, you know the die, so you have to tell what's even, what's prime from the die. In this example, everything is given in the Venn diagram, and in the first example, all the percentages you need is given. Okay, but here in this example, some numbers are given and some you have to maybe predict yourself or so. So there is 2 ways to solve this question actually. There's 2 ways to solve this question. One way is I can build a table like this. One way is to use this information to build a table like this. And another way, I can just directly apply the addition rule. I can directly try to apply the addition rule. So let us look at the 2 ways, and then again, your choice. You choose which way is preferable to you. Okay, let's look at the 2 ways and then see which one is preferable to you. So I need to open a Word document here. Now where's back there? Sometimes. Okay, so one way I will actually okay, let me just type the information and then we see what we want to do after this. Sample 100 wood, so we have 100 wood. Okay, 100 wood. Type and plus 100 graffiti. Okay, tennis rackets. That means what? That means total 200. That's the first step. Okay, the total of wood and graffiti is 200. Type. Now 11 wood and 19 graffiti are defective. Does it mean an extra 11 wood or 11 wood from the 100? Now if 11 wood and 19 graffiti are defective, does it mean 11 wood from the 100 or extra over the 100? What do you think?
From the 100.
From the 100. Okay, so some of these 100 are defective. Defective means they are not good. They're not working. Yeah, and some of them are not defective, which I'll just give it a simple D bar. So the defective from the 100 are 11. So that means the good ones that are not defective is obviously what? 89. So we can make this analysis as we go. We can make this analysis as we go, as we read. And I said 19 graffiti are defective. So the 19 graffiti, the 100 graffiti, some of them also are defective, which are 19. And some of them are not defective, which are remaining from 100. So 100 minus 19 will give you 81. Clear now? So now we have a pretty good picture about the total number of rackets, how many graffiti, how many wood, how many defective, how many not defective, and everything. Now we can continue reading and understand what's the question one. Okay, now we are saying one racket is randomly selected. From all these groups, one is selected. Find the probability that the racket is wood or defective. Now this is the question. The probability the racket is wood or, let me just write wood properly, W, okay, or defective. So that's the question. So the first thing maybe comes in your mind, I'll just apply the rule. Okay, so it's the probability of wood plus the probability of defective minus the probability of being wood and defective. Okay, so in this case, with the analysis that we did with all these numbers, hopefully now things become a little bit easy. So the probability of wood, you can easily now find out the total number of wood, which is 100. And this is the total number of wood, and we're selecting from the whole. What is the whole? The whole pack of rackets is 200. So we know now the total is 200, so we can divide by 200. Okay? Time. Next, how many defective we have? How many defective?
30.
30. They come from where? They come from the 19 and 11. The 19 that are graffiti and the 11 that's wood. That's what I care about, defective. All the defective. Not just the wood, not just the graffiti, together. All the defective. So all defective items are 30. It came from the defective of the wood and the defective of the graffiti. And of course, we again selecting from the total, so we should be dividing by the total to get the probability of defective. Finally, the last one is the wood and defective. And remember, the and here is the intersection of the common path. So I'm just going to write it again to remind you. The intersection or means, it actually means at the same time. At the same time. That's what it means. Okay. So in this case, I am looking for the wood and defective at the same time. How many wood and defective at the same time? If you see that branch of the wood, there's 11 defective. So it must be this 11 defective that are from the wood. And again, I divide by the total. So this way, I was able to solve the question applying the rule. This way, I was able to solve the question when I applied the rule. Okay? Leave this type of solution or this choice. But that choice requires you to analyze the problem from the beginning. Whenever you read a number, as you read, you just break it down into parts and make sure you have the total as you go so that you have all the numbers ready when you apply the rule. This is one type of solution. The other type of solution is I would build a table. Okay, another solution is that I will actually build the table itself. So I have tennis rackets. Some of them are wood, so I'm just going to write the wood here. And some of them are graffiti, so I'm going to write the graffiti here. And some of them are defective, so I'm going to just write defective here. And some of them are not defective, so I'm just going to write D bar here. It's not defective. Okay, the total of the wood is 100. So maybe I can just write the 100 somewhere. Maybe you can write next to it, or you can just write it as a total at the end. Yeah, this is total. The total of the wood is 100. Okay? The total of the graffiti is also 100. That's what he said in the beginning. Type, how about the defective? He said 11 wood are defective. So from the wood, there are 11 are defective. And he said 19 graffiti are defective. So from the graffiti, also there's 19 defective. So we write these numbers here. Obviously, if you know the total, you can easily get the defective ones. The defective ones are going to be 100 minus 11 here, which is 89, and here 100 minus 19, 81. So this way I built the entire table, and now I can get the probability of the OR without actually using the rule, because everything is in front of me now, is in front of me laid out nicely in the right place. So I can just use it to get the answer. So the probability here, he wants wood or defective. Okay, or let us write the D nicely as capital D, since we here using capital D in this one. So let us use capital D also. Okay, and then let's look for the defective and wood. The wood are here. This is also wood. How about the defective? The defective is here. We can use another time shading, but we don't count it again. And then the defective is also here. So the ones that I just highlighted, these are the ones that are wood and defective at the same time, as you know, when you combine them together. So that means it will be 11 plus 19 plus 89 over the total, and we said the total before is 200. So here I didn't need to apply the addition rule, but I used the concept of the union. The union, I just make them all united. Sorry, this part is united. Maybe I just use another color. Yeah, this is now the union of the wood and defective. These three numbers in the union. So I just was able to collect the number of the union and justify it by the total as another way to solve the question. So I hope that was clear, this question, because a lot of people were asking me yesterday about it. Okay, all right, any questions here? All right, so that was another example of using the addition rule. Okay, we have a couple more. Question 6. Question 6. Let A and B be events that such that probability of A equal to 0.4, probability of B 0.5, probability of A or B equal to 0.7. Find the probability of A and B. This question is a theoretical question. Okay, there is no names, there is no story behind it. It's just I'm giving you probability of A and B. This is just like arbitrary chosen events, or assumed that we have A and B events. This is the probability of A and B. Here's the probability of the OR. He wants the probability of AND. Now that should be easy, because I can just substitute all of these in the equation and just try to solve the equation. The only difference in this example is that the OR now is given and the AND is required, so I have to solve the equation. I have to solve an equation for this. So maybe I can do this here. We know the probability of A or B is equal to the probability of A, okay, plus the probability of B minus the probability of A and B. So in this case, what is given is the probability of A itself, which is 0.4, the probability of B itself, which is 0.5, the probability of the OR is given as well, which is here 0.7, and now I need the probability of A and B.
Doctor, it's minus A and B.
Ah, yes, thank you. So in this case, I need the probability of A and B. I just need to move this term with its sign to the other side. That's how we solve the equations. So it will become positive on the left, the probability of A and B. and meanwhile move this number to the other side, and which will become negative, because when you move terms from one side to another, the sign will change. The sign that's before the term will change. Okay, so this will be 0.4, okay, plus 0.5 minus the 0.7. And in this case, it becomes easy to calculate, right? And that equal to 0.2. So I was able to get, I don't know why, the probability of the AND. I can actually ask you for the probability of A and give you all the other three. Or I can ask you for the probability of B and give you the other three. This equation is 4 unknowns. It's connecting 4 quantities together. So in this kind of theoretical questions, I can give you any three of them, and I ask for the fourth one. So here I was asking for the probability of AND. Maybe another question, I ask for the probability of B, and I'll give you the probability of the AND. Or maybe I give you everything, but I ask for the probability of A. Any of these are possibilities. All what you have to do is just plug in all these numbers into the equation and try to solve the equation for the unknown, which I think is easy linear equation. All of you have taken before, and you probably, hopefully, you know it very well how to solve these kind of equations. Okay, so that's question number 6. That's a new type of questions that can come on the addition rule. Question number 7 that we have here, which is our last question today, is, let us see, what does it have? He now wants you to draw a Venn diagram of the union of A or B or C. That's a very easy question. He just check if you understand the union, the concept of a union, and if we generalize this to more than 2 events. Like here I have 3 events. So A and B and C. If you have A with B with C together, I want the union. So how is it going to look like? What is the shading that will look like? So that in this case, we have A or B or C. We have 2 cases actually. We have one case when they are maybe more than 2 cases, but generally speaking, we can explain 2 cases. One case where they have overlap, one case when they don't have overlap. So if I have A, for example, here, and maybe B has for example here, and C is here. Suppose this is A, this is B, this is C, and then I want to shade the OR. I want to show the OR. The OR will be, what do you think? Is it going to be the part that here in the middle? Like for example here? Everything. Yeah, everything. So everything has to be shaded. This will be the union. This will be the union. So the union is everything. Yes. Very good. So that's now A or B or C, because the common part is only the AND part, and here we are talking about OR. The other case we could have is that we have them mutually exclusive. Remember what mutually exclusive means? That means they are disjoint, or they are separate. Yeah, they are separate, they don't overlap. So you can have this case where A is here, the B is here, and the C is here, and they don't overlap, right? In this case, if I want the union, can they be united when they are separate? Yes, they can still be united when they are separate, right? In this case, we're going to share everything also, but this time A and B and C are not overlapping. So this will be the union in this case of A or B, sorry, okay, or C. But the difference is that here we have them mutually exclusive. This is called mutually exclusive. While here they are not mutually exclusive or non-mutually exclusive. Okay. All right. So I think that will conclude today's workshop. Small discussion about, maybe I'm here in the answer. I have only one of these solutions, but there's actually another one I showed you with their mutually exclusive. Just to show you that there's a variety of questions that can come in any rule, and that's just the nature of probability. And here I'm talking about the addition rule. If I talk about the multiplication rule, then maybe instead of having 7 questions, maybe I have 17 questions. I don't know how many they will be. There will be a larger number of questions that can apply here. So does anyone have a question or like to ask me something? Does anyone have a question? With the idea now of the addition rule clear, the concept of the union and addition rule is clear, and different applications, different examples.
Yes, doctor, it's clear.
Okay, very good, great. So I guess we're finishing a bit early today than I expected, but I hope you got the point, and maybe we can do another workshop for the multiplication rule next time, which maybe will have I'll show you the variety of examples that we can look at in this case. Thank you for attending today, everyone. I really appreciate the people who organized this workshop, and I hope it was beneficial. Assalamu alaikum wa rahmatullahi wa barakatuh.
Alaikum salam.
Thank you.
You're welcome.